We are now recording, and here's this. Okay. We'll go from this slide. I didn't bring the one sort of announcement that was. I don't know if any of you are interested in it. Possibly one. But yesterday was a grand opening, ribbon cutting, this kind of stuff, ceremony for 2 new buildings on campus. One just on the Birmingham West campus, that new Academic Success Center. That was opened yesterday officially. People have been moving in for a while. And also yesterday, official ribbon cutting for the dorm, residence hall right next door. The one they've been working on probably most of the time you've been coming. So both of those, are you in the residence hall? The other one? Yeah, okay. Have you been in the new one yet? Okay, I haven't either. Huh?
I might go in there today.
Yeah. It looks pretty nice from the outside, but of course yours looks really nice too. It's a fairly new building as well.
Yeah.
Being built since I've been working here anyway. On the Bessemer campus, there was one addition done to one building, but that was before we merged, and nothing else has been built there since. So there's quite a bit more building going on here. But anyway, that has occurred. And then there's one other bit of news, or I guess just an announcement. It's one of these good news, bad news situations. The good news is next week is spring break week. But the bad news is that means we won't be meeting next Wednesday. Sorry about that. Get over it. Hey. That's terrible news, okay?
Right, well, we get another teacher or something.
All right, so let's pick up and go from here. Any questions on anything else before we get started? All right. Okay, last time we were in chapter 16, and we are very close to the end of 16. That's why there's no more slides in 16. We had talked about the Ferris wheel and other springs, other things that follow simple harmonic motion. Here's one more object, and this is called a pendulum. And I think probably most of you know what a pendulum is. It's something suspended from a point, and it goes back and forth in an arc. Okay? Think grandfather's clock or grandmother's clock or something like that. I didn't draw that very well. Let me see if I can improve on that a little bit. Okay? How's the foot and leg?
It's doing good.
Yeah, it sure seems like it.
I get cleared.
Get cleared what?
To play again
Next week? What position?
Third base.
Third base. Boy, you needed a lot there. Okay. That's still not a very good arc, but you get the general idea. Okay? So a pendulum consists of an object suspended so it swings freely back and forth about a pivot. The pivot is the thing at the top. Pendula, they call it pendulums, have been commonly used in clocks for many years. The motion of a pendulum with the displacement, when the displacement is small, very closely approximates simple harmonic motion. There are 3 basic properties of a pendulum discovered by Galileo. And, all right, here's Cerdarius, right? All right. Pretty good crowd today. The pre-spring break class. Okay. So here are the 3 basic properties of the pendulum. I'll get this ugly picture out of the way now that you have a general idea what it is. The first of these, the period, and by the way, period, just like before, is given the symbol T, measured in time. Usually capital T is temperature, not in this case. Capital T is period. The period is independent of the mass. So it doesn't matter how big a mass you have on there, the period is not going to change any with that. Okay? Now, air resistance is more affected by the size and shape of the bob than is the mass. Okay? So air resistance may be a bigger factor, but not. Now, if you think of a grandfather clock, it seems to have a great big old thing at the bottom that swings back and forth. So is that to get it more massive? Well, no, it's mostly decor. But if you look at it from the side, that big old thing is very, very thin. That way, the air resistance is minimized. Okay? So, irrespective of the mass. The period is irrespective of the mass. Number 2. Okay? The period is independent. And by the way, independent means doesn't depend on, okay? Bigger mass doesn't change the period, okay? The period is also independent of the amplitude, okay? When the arc is small. Okay? That is when it's less than 10 degrees. That's pretty small, okay? Now, that means it doesn't help to swing it up to here and get it going, or to swing just a little bit and get it going. It's independent of either one. It's independent of how high you initiate the pendulum, okay? And number 3, third thing discovered by Galileo many, many, many years ago, subject to those conditions, the less than 10 degrees, that kind of stuff, the period is given by, so here finally they give you the period. It's 2 pi, that's as in dealing with a circle, and it is somewhat of a circular arc there, times the square root of the length of the pendulum divided by the acceleration due to gravity. Okay? So T is the period, as I've been saying, okay? And that's usually measured in seconds. It's a time period, okay? The L is the length of the pendulum. That's usually meter or feet. Meter in the metric or SI units, feet in the U.S. customary, okay? And G is the acceleration due to gravity. And of course, if you're measuring the length in meters, then this would be in meters per second squared. In fact, I'll don't just give the units, I'll give the actual number. Anyone tell me what that is? Yeah. 9.80 meters per second squared, or, I shouldn't put that. Say again? 9.8 meters per second squared, or in feet per second squared, it's 32.2 feet per second squared. Not just the units, the whole number. That doesn't change anytime you're on anywhere near the surface of the earth, which is where we live. Okay? Now, so the period depends only on the length and the acceleration due to gravity, but of course, if you're anywhere on the earth, that's a constant. Okay? The longer the pendulum, the longer the time for each complete swing or period. The less the gravitational attraction on a particular planet or moon, the larger its period. So it's the inverse relationship. Directly related to the square root of the length, inversely related to the square root of the acceleration due to gravity. Now, we have, I guess it's called the grandmother's clock. It's a shorter one with a pendulum. And I could not ever get it to operate fast enough. I screwed up the thing the whole way trying to get it to decrease the period so the time would be shorter. I couldn't. It always ran slow. So I always set it a little bit ahead, and then figuring that, you know, by the time the spring ran down, it would be just a little bit behind. So I tried to keep it, but then it got so it didn't work very well at all. But it's a nice looking thing. It was a gift to us from my parents-in-law. They gave it to us for Christmas one year. All right, there is just one example here on this one, so let's do that. And we will be through with chapter 16. Find the length in centimeters, that's different from what we said before, of a pendulum with a period of 1.50 seconds. What stands for period? What's the parameter? Capital T, 1.50 seconds. And it says find the length, so we're looking for the L. Now, they say in centimeters, okay? Our formula was in meters, or feet, but we want the meter part here. So, what's the other part, the only other thing it depends on? Acceleration due to gravity, and since we're going to be dealing now, here's where you have a choice, folks, okay? You can either change gravity, which what is it normally? 9.80 meters per second squared. You can either change this to centimeters per second squared, or you can work the formula, solve for L, and it's going to come out in meters, and then change it to centimeters. So you got to make the change one place or another. Really, it's not too bad to do it here. So how could you convert that to centimeters per second squared? But per second squared is not going to change, only meter to centimeter. So what unit is going to go where? Always, I put two blanks here, numbers go here, units go here, always put the units in their place. What unit goes where? One goes above, one goes below the line. Which is? I couldn't hear. Okay. Well, see, meters already on top, so you need meters on the bottom, so it'll cancel out, and that leaves centimeters on top, which is exactly where you want it to be, right? Now, once you get the units in their place, then you say, how many centimeters in a meter, how many meters in a centimeter? 100 centimeters is exactly 1 meter. How many cents in a dollar? 100. Okay? So this will be multiply numerator dividing by denominator. That's only 1. So this will be move this decimal 2 places to the left, 980 centimeters per second squared. With that in mind, we can go to our formula. Now, would you all rather solve it literally, for which we're looking for, L, or you want to plug in all the numbers and then solve it? Doesn't matter which way. The book usually likes you to solve literally first. Frankly, I find it a little easier because you got to do the same operations, and if you carry all the numbers around, that's just extra numbers and units. So let's do, what is the basic formula? T is equal to 2 pi, the square root of L over G. Okay? I've got a sneeze, sorry. Y'all awake yet? All right, good. All right. Now, we're wanting to solve for L. So one thing let's do, before we start messing with the square root that we got to mess with, let's get rid of the 2 pi. So let's divide both sides by 2 pi. Now pi is just a number. That's not that has no units or anything. So the 2 pi's have gone from the right-hand side. They're moved to the left. Now we need to get rid of the square root sign. How do we do that? How do you undo a square root? Square it. So let's square both sides. That will wipe out this, but that means you square everything here. Okay? And now the one last thing to do is get rid of the G. So we'll multiply both sides by G. Okay, so what we have left is L is equal to, and this will be in centimeters because we changed the G to centimeters. Oh, and the G's go out here. That would be G times T squared over 4 pi squared. I went on and squared both of those. Okay? Well, G, we're going to use this one, 980 centimeters per second squared times your 1.50 second squared over 4, I've already squared the 2, and then pi squared. Okay? Now, another thing you could do is just wait and square that all as 1 unit. That may be easier to do calculationally, so let me write this another way. 1.50 seconds divided by 2 pi, and we'll square the whole thing once you've done the calculation. That's probably a little bit easier than having to square everything. Okay? So, we won't do this part, we'll just do that. Okay? Now, let's see what happens to the units. Notice here we have seconds squared, and here we have seconds squared, so that's going to end up in centimeters, just what we want the length to be. We want the length in centimeters. So pull out your handy-dandy calculators or computers and do 980 times, now open a parentheses if you got one, and do 1.5 divided by 2, and divide again by pi, if you have a pi key there.
Close the parentheses before you
After you, no, okay, here's how I would do it. 980, okay, 980 times, okay, open parentheses, 1.50, you don't have to put the 0 there, 1.5 divided by 2, and then divide that by pi. That's the same thing. You're just dividing twice. It's the easiest way to do it. Close your parentheses, square that, and then hit the equal sign. And see what you get. 55.85 is what you said. That would be in centimeters. That sounds like a reasonable number. Let's see what they got. They got 50, did you say 0.85 or 80?
8.5.
Oh, 8.5, okay. I'm sorry. I misunderstood. I think I even said 5, but I wrote 0. I don't know why. And 0.85. Well, we only have 3 significant digits there, 3 significant digits there. 2 is to as many digits as you want. Pi goes for forever. So let's only do 3 significant digits here, which is approximately 55 point. The third digit is 8. Look to the right. 5 or greater. Move that up to 9 centimeters. Okay? So that's about the length of the pendulum that it took to give you a period of 1.5 seconds. 1.5 seconds. Okay. Now, by the way, and now they did it all in meters and then converted that to centimeters at the end. Came out the same way both ways. What was I going to say? By the way, the period. That's not for it to go from here to there. It's to go from here to there and back there to the same starting point. That's 1 period. So that's 1.5 seconds. All right, that finishes 16.6. You can do any of the odd number exercises 1 through 13. And that finishes the chapter. There's a good glossary there you can look at, review your words. There's your formulas you can use. They're all given there. And then review questions are pretty good. They're just mostly conceptual things, but your review problems will be more like what you see on the test, and those will be any odds there from 1 to 17. Then there's what they call an applied concept, and this is a very interesting picture. If you got your text, the one on page 450, if you remember when we talked about resonance, that was a bridge. It's called the Tacoma Narrows Bridge, built across Puget Sound in Washington, formed a standing wave before it collapsed. You see, it was a big, fancy looking, really looked like well-constructed bridge, but it happened to be just built so that its frequency, natural frequency of the bridge, resonated with the wind that came through there almost constantly. And when that happened, the bridge started rocking, just like when you're pushing a kid in a swing or pushing a car to get it to jump start or something like that. It resonated just so it started the bridge moving, oscillating, and it just kept getting stronger and stronger until it literally tore itself apart. There were cars on it at the time. They went crashing into Puget Sound. Okay? It was a terrible experience for civil engineering. From then on, they always took into account prevailing winds and made sure their structures were not on a natural frequency of the prevailing winds. They did not want that to happen again. Big black eye to the civil engineers that did that. All right, now we move to basic electricity. So let's clear this slide. Any questions on chapter? Oh, anyone here who did not get the test last time? We were close enough to finishing last time. I ran off copies of the test. This chapter 16 test. Okay. I hope everybody's gotten the first test, second test, and third test. This will be the fourth test, right? All right. 1,
This is on 4, right?
2. This is chapter 16. Okay. Did all the rest of you get chapter 16 test? Okay, I'll get it. Here, hand her one.
I don't have the third one.
You don't have the third one either? Okay.
I just finished the second one. This stuff is.
Okay. All right, there's the third one.
What one? The fourth one?
Yeah.
Which one is this? The fourth one?
That's the fourth one. This is the third. Okay, everybody got all 4 tests if you haven't turned them in already?
Are you still grading the other ones?
No, I've got everything graded that's been turned in so far. I may not have everything on Blackboard yet. Okay, but you can certainly see your test and the grade if you want to.
Yeah, I was looking at the place.
Okay. All right, I can't return them until I get them all in, which, now that we're recording, let me put that out there too. Okay? Test 1. One person has not turned that in. She's not here. She hasn't been here much at all lately. Okay?
She probably dropped.
Well, she hasn't dropped. That's the problem. She probably needs to drop. Okay? Test 2. I've received 2. Okay, we got that. Okay. All right. Test 3. I've received 1. Okay.
I bet you the only one I did. What?
All right.
Test
Good
2.
deal.
Test 3.
Yeah, test 3, yeah.
You did test 3 hours.
Yeah.
All right. So there is, I've got test 2 and for 2 more people. Fantastic, folks. Now, for those who just got the next 2 tests, let me point something out. I've made the corrections on there, but just so you'll be able to read and understand what those corrections are. Okay? Let's do test 3 first. That's the one that says, whoa, goodness, where is it? All right, this is discons. Oh, I see what's happened. Wait a minute. Some things got out of order. Okay, now we're back. All right, test 3. Those who just got test 3. Number 3. That question makes no sense. the vertical steel columns in an office building each support a weight of 50,00 pounds. That number makes no sense. I worked it to see if they meant 5,000 pounds or 50,000 pounds. The answer supports 50,000 pounds. So it's 50,000, 50,000 pounds, each being compressed, blah, blah, blah. And then the B part says what would the compression be if the weight were 60,000 pounds, not 6,000, 60,000. So that's another 0 in that. Okay? So that's test 3. Test 4. The number 8 and number 9 left off the frequency of the whistles or whatever, horn.
I'll return mine in, so.
No, this is test 4.
Which one?
This one, test 4, the one I just gave last time.
Okay.
Okay? This is number 8. A train traveling at a speed of 80 miles per hour approaches the observer of the station and sounds a whistle, but it don't tell you the frequency of the whistle. That whistle is at 585 hertz. That's what I wrote on this margin, but that's what it is. The whistle's frequency is 585 hertz. And then what frequency is heard by the observer, and there it gives you the speed of sound in air. Number 9, same thing. They even put frequency of and left it off. So the car traveling away from you at 70 miles per hour, the car horn produces a sound at a frequency of, and they left it off, 5,000 hertz. What frequency do you hear? Okay. So those are the 2 corrections. I made them already, but so you'll understand what they are. Okay. Good deal. Now, ready now to go to, anyone need this up here a little longer? Everybody got it? So erase that, and let's go to basic electricity, okay, from current slide, chapter 17. Now, we're not doing the whole chapter, okay?
So it's pretty long.
It is a very long chapter. We don't have time to do it all. We're doing, we're actually not even going to start in 17.1. I'll just give a little bit of introduction there, but we're actually starting in 17.3. Your homework, or you'll be tested on 17.3, 17.4, 17.5, 17.7, though we've got to do a little of Ohm's Law, 17.8 and 17.9. You can't do, huh? Yeah, 3 through 9. There's nothing that says you have to do Ohm's Law, but some of the problems in 7, 8, and 9 require you to know Ohm's Law, so I'll go and give you Ohm's Law as well. Okay. So, let's just look at a few key terms here and a few key concepts. I'll just go through basically what they show you in the slides. Okay. There is a little blurb mentioned about Benjamin Franklin. And you might say, wait a minute, he was a politician, wasn't he? He was one of the authors of the Declaration of Independence. He was one of the authors of the Constitution. He was the first Postmaster General. He was a publisher, Poor Richard's Almanac. He was an ambassador to France, I know. He was a general all-around patriot, okay? What's he doing in a physics book? He was also a very good scientist and engineer, okay? And in fact, he's the one responsible for calling electrons negative and protons positive. Didn't matter what you call them, he's the one that sort of designated that, and there are many of us who think, I wish he'd have done it the other way, okay? But anyway, I'm not going to go over this, don't sweat this much too much. This is a naturally looking atom. Okay? Now, not quite, but close to it. In the nucleus are protons. There's also neutrons there, but neutrons have no charge, so they're not showing the neutrons. This one, if it is indeed what it looks like it is, it's a lithium atom. Okay? Lithium atom has 3 protons in its nucleus. Now, the problem with this picture is the nucleus, okay, the relative size of the proton to the electron is probably understated. The proton is much more massive than the electron. In fact, the electron has almost no volume at all. It would just be a little dip on the page. That's all. They've really expanded that. The protons, accordingly, are quite a bit larger than the electrons. But massively, they are 10,000 times more massive than the electrons. So size-wise, they're bigger, but mass-wise, they're hugely bigger. And the neutrons that they haven't shown here are even slightly more massive than the protons. Okay? So all of your mass lives in that tiny, tiny little tightly packed nucleus. And the electrons are out here flying around in a cloud, and they have almost no mass at all. But we're not concerned with the mass right now. We're concerned with the charge. The protons are positively charged. The electrons are negatively charged. Okay? And even though their masses are incredibly different and their sizes are hugely different, they each have a charge of 1. +1 for the protons, -1 for the electrons. The neutrons, the biggest of them all, don't have any charge at all. Okay? So charge does not take up very much weight or mass. Okay. So this is an uncharged lithium atom. It has 3 protons, 3 electrons. Now the electrons aren't quite drawn properly either. If it were drawn properly, you would have a pair of electrons on the inner shell and just a single electron flying around out here on the outer shell. But they weren't trying to do it spatially right, they just were showing you the number. Now, because the 2 on the inner shell are basically along the same path there, they're very happy just hanging around with each other, not really close, but just in the same shell. The one on the outer shell is way out there by itself, okay, all alone. And the nucleus is really tiny in here. It's not felt very much, so it's real easy for lithium to lose that outer electron. Just lose it, okay? And that would form a positively charged ion. It's not an atom anymore, it's now an ion. It now is a +1 because it has 3 pluses, only 2 minuses, so it has a +1 charge. This never happens, but they're just showing it for illustrative purposes. If lithium would pick up another electron, then it would be negatively charged. Lithium doesn't do this, but many other atoms do, okay? But they're just showing this for a purpose. So this would be a negative ion with a net -1 charge, okay? So that's where we get our charges. Electrons or protons, okay? Now, notice this.
I'm sorry to bother you. Did anybody think they dropped any money outside? Not a whole lot, but you did?
I didn't understand what she said. I said, maybe. No, but
Yeah.
I wouldn't have said that. Okay. All right. Now, notice here. For an ion to be positively or negatively charged, can it lose a proton or gain a proton? No. That requires a nuclear reaction, and then it's no longer what it is, okay? The only way it changes charge is gaining or losing electrons, those tiny little things that fly around way on the outside. That's the only way charge is exchanged and things are charged. Gaining or losing electrons. Okay. Now, this is just how electric charges work. And we're just going to do this real quickly. You're not going to be responsible for this. This is called an electroscope, by the way. If you have a ball of wood pith, basically something like cork or something like that, there. And you have a rubber rod, and that rubber rod you had gotten something like wool or fur or something and rubbed on the rubber rod, what you do is wind up knocking electrons off the fur or the wool onto the rubber. So now it becomes negatively charged. So this ball is neutral, no charge, but you take this rubber rod that's negatively charged, touch it to the ball, suddenly it becomes negatively charged because electrons try to disperse themselves as much as they can. If you do this to two electrodes, electroscopes, and then get them close to each other, they try to get far away. Because why? Like charges repel each other. Like charges repel each other. If, however, you had a glass rod that you rubbed with silk, okay, that is going to take electrons off the glass. The silk picks up electrons from the glass. So now the glass becomes positively charged. They've lost electrons, and you touch that to that neutral pith, ball of wood pith, let's just call it quartz, and you hold it next to one of these that are negatively charged, and now they start going toward each other, because unlike charges attract each other. Unlike charges attract. But if you did that to a second electroscope, and then held it close to the other one, the like charges repel each other again. Basic principles of charges. Like charges, whether they're both positive or both negative, they repel each other. Unlike charges, no matter which is positive, which is negative, as long as they're unlike, they attract each other. Okay? Now, here's a fancier looking electroscope. Okay? Has a metal ball on top. Now, the deal with the other, wood, glass, rubber, they're all non-conductors. They don't conduct electricity. So whatever charge you put on them stays on them pretty much. This metal, however, does transmit electric charges very easily. So now we have two gold foil leaves here. Okay? I don't know why they chose gold foil. I guess it works pretty well. It's pretty expensive, okay? And you have them, they're just hanging side by side. No charge on them at all. You have a metal ball, metal stem. This, though, is an insulator right here, okay? Not metallic, not a transmitter of charge. But the metal stem is going through that. You've got a metal case. It does have a glass window. You can't see it because it's clear. And two gold leaves in the middle. This is called a gold leaf electroscope. Now, if you take a rubber rod that's been rubbed with fur or wool, so it's become negatively charged, and touch it to this, no, I'm sorry, don't touch it. Bring it close to that. Because the metal conducts electricity, or the charges really, really well, because this is negative, the positive charges from this whole operation go up and try to neutralize those negative charges. You haven't let them touch, you just brought them close by. And as soon as you do that, you've taken basically what's happened. This is extra electrons on it. This, all the electrons trying to get as far away as they could, including on the gold foil. And since both of those have extra electrons, they repel each other. And you'll actually see that happen. You haven't touched the thing, okay? You just rubbed this and became a negatively charged rubber rod, just brought it close to it, and there those go apart, okay? Or, take it away, they go back together. Then bring a glass rod that you rubbed with silk, so it's become positively charged. Bring it close by, don't touch it, just bring it close by, and there goes the gold foil leaves again. They go spreading apart because they're now positively charged. Because this being short of electrons, that's why it's positively charged, deficit of electrons, these electrons from down here go rushing up there to neutralize that, and though you haven't touched it, and that leaves a deficit of electrons here, so it moves apart. So that's how electric charges move. They move through conductors, they hang steady on insulators. Okay? Now, here we're doing something different. This is more than I thought they were going to do. Okay, you're bringing the negatively charged rubber, okay, close to this, and that becomes positively charged, they move away. Okay? Now, you haven't let this touch, but what you do, you touch it. Well, what are you? You're grounded, and therefore, you have, they have it backwards here. Electrons leave your hand and try to neutralize that positive charge, and the leads go together, because now you've made it neutral, because you're neutral. Okay? The electron arrow should be going the other way. Okay. So this is now neutralized. Okay, sorry. It's neutralized, but the whole process, electrons left your finger to go to this positive part here. So actually, this is now negatively charged, but that's negatively charged, so it doesn't respond at all. So, doesn't respond, pull that away, and now, because that's positively, they have this so backwards. Okay? Sorry. Maybe they meant these to be plus charges here. I don't know. Let's just skip this, okay? Because this is backward. This would be exactly right if it was this case, okay? Then electrons would be leaving that going to ground. And this showing a positive charge. So rather than argue with them, let's just go on. This is a device called a Van de Graaff generator. Okay, what it has is a sort of a fabric or some type of a belt here that goes very, very fast, and there's brushes under here you can't see, and those brushes are knocking off electrons off of the fabric, and they get distributed all around the metal here. Okay, and if it starts off being neutral, but then when you turn it on, it gets negatively charged. So what they do, these kids have gotten up there. Now, what they were required to have is clean hair, a little bit longer hair. It won't work with me, never mind, at all. But clean hair, dry hair, okay, and usually dry conditions too, not too much humidity in the air. It may not work in the South as well as it does other places. And they're putting their hands on it, then they turn it on. They don't feel a thing, but except they feel the hair start doing this. And why? Because those negatively charges go to all parts, including their hair, and now the hairs are negatively charged, so they try to get as far apart away as they can from each other. So basically their hair becomes an electroscope. Now, they should not take their hands off that ball, then they will feel a charge. So they wait until they turn the machine off, and someone neutralizes the charge on it, then they can take their hands off. They need to be standing on an insulating platform so they're not touching the ground, or else they would feel a charge there as well. Okay, so that's your, all right. I think now is about where we really do pick up. That was basically your 17.1, 17.2. That was called induction, by the way. And now we're 17.3. And didn't I say we started in 17.3? Okay. Yeah. Coulomb's law. This is where we begin here. Now, a couple things. Robert Van de Graaff, physicist, guess what? Born in Tuscaloosa, Alabama. Yes. He invented the constant potential electrostatic generator, later known as the Van de Graaff generator, and later developed the generator for use in particular accelerator. He invented the insulating core transformer in the late 1950s from Tuscaloosa, Alabama. Now that was 1901 to 1967. I was sophomore in high school that year. Okay. And then, yeah, I'm that old. Okay. It's not that funny. Okay. Charles Coulomb.
I know that my mom was
What's that?
my mother
Oh, really? Okay. So she may be almost as old as I am. Okay. Okay. Charles Coulomb was a physicist born in France, pioneered research in electricity and magnetism. Notice his years of action. He was born in 1736, died in 1806. Now that's a little, hopefully he died of natural causes. The reason I say that, I mean, he lived to be 70, and that was pretty long back then. But the reason I say that, does anyone know what was happening in around the early 1800s in France?
It was the
French Revolution.
Yeah.
And the French Revolution was one really famous for the guillotine. And if you didn't agree with the guys operating the guillotine, you may have lost your head. Now, I don't think that happened to Coulomb. I don't think scientists got involved too much with that. But anyway, he was. Now, remember I said Benjamin Franklin was ambassador to France. Benjamin Franklin was a big heavy in developing electricity. I bet you he interacted with Charles Coulomb to a significant amount. Okay? I don't think there's any way it could have avoided that. They were too much involved with the same type stuff. So, this is a little before we're getting to, so let's start with Coulomb's law. We're leading to this right here, but we haven't quite gotten there yet. The charge on a proton is denoted by this symbol, okay? Now, protons are which charge? Positive, P, proton positive, okay? So we call it E plus. That's electron with a positive charge. I mean, it's not electron. It's electric charge, one positive electric charge, okay? Charge on a proton. Each proton is one plus E. The charge on an electron then would be E minus. E stands for the amount of charge, plus means the positive amount, minus means the negative amount. In the study of electricity, now this is the individual charge on an individual electron, individual proton. That's way, way, way too small for us to ever detect or measure or do anything with. So what we do, we use a much bigger charge. In the study of electricity, a much larger unit of charge is required, and it's called a coulomb, named after Charles Coulomb of France, because he's the one who first studied them. And because it's named after somebody, the symbol is capital C. Now, we're not going to get into temperature, but there was a Swedish, I believe he was, scientist who developed a scale to measure temperature, and that was named the Celsius scale. So that also uses capital C, but with a Celsius temperature, you have to use a temperature symbol, the little degree symbol. So that's how you tell coulombs from Celsius. Celsius always had the degree symbol. Coulomb does not. Okay? And they're talking about totally different things here. So, the measurement of the unit charges gives this. One electron charge is plus, because this is positive for a proton, I said electron charge, but a single charge is plus 1.60, get this number, times 10 to the minus 19 coulombs. Coulomb's a big macroscopic quantity. Electron charge or a proton charge is a very incredibly small microscopic quantity. Okay? Whereas the negative electron is the same number, but just a negative 1.60 times 10 to the minus 19 coulombs. Now, said the other way, 1 coulomb would be involved with the transfer of the reciprocal of this, 6.25 times 10 to the 18, either electrons or, well, it always would be electrons. If you're gaining the electrons, that would make a minus 1 coulomb. losing electrons would be a plus this number of 1 coulomb. So that's how many electrons you'd have to be moving. Now, in order to get a good perspective of that, this would be 6, 250, 000, 000, 000, 000, 000, 000, electrons. I don't even know what number that is. This would be 1,000, that would be million, that would be billion, that would be trillion, that would be whatever quadrillion, and whatever follows a quadrillion, centillion, is a huge number. That's how many charges, electron charges, it takes to make a single coulomb of charge. And that's not a very big charge, but it's measurable. So that's what we're dealing with here. That would be the amount of charge that passes through a 100-watt light bulb in about 1 second. So that's a lot of charge, okay, because electrons have very small, very, very small charges. Now, in 1789, and that may have been about the time Franklin was over there, I wouldn't be surprised, Coulomb made a scientific study of forces of attraction and repulsion between charged objects with a very sensitive torsion balance. From his experiments, he determined the existence of the inverse square law. I think you may have heard me mention that before. If you have, say, a charge here, if you move this far away, you decrease the amount of charge because the distance traveled. If you double the distance, you decrease the charge sense that you sense by 1/4. If you increase the distance, double it, the charge sense is decreased, inverse, squared by the square. So it would be 1/4. Okay. All right, take care. Now, I'm going to need this slide soon, but not yet, so I think I'll go back to my other one so I can write more on it, okay? Also get my pen color back. All right. Now, here's Coulomb's law of electrostatics. Now, what does electrostatics, what does that mean for you?
Electricity from static.
Okay, you're really close. It's charges that are not moving. You've charged something like we did that pith, and stuff, put the charge on it and then leave it, and it just sits there, hangs there, okay? As opposed to electricity you plug into the wall and charges are always moving. So it would be like static electricity. In your dryer or something like that.
So that's like when your phone not charged, but it's plugged up.
Okay, no, when your phone is charging, you're moving electrons into it. Okay?
But if it's not charging, it's just plugged up.
Oh, okay.
Like
Okay, I sort of, okay, I see what you mean. You reached 100% charge, so it can't charge anymore. That would be similar.
Since I've been here, my phone charged.
It's not charging. So that's why that brought that up. Okay, I see. It's more like when you comb your hair with a rubber comb, and then you pull the comb away and it pulls your hair away, not because it's tangled, but because it's the comb is now negatively charged, your hair is positively charged, and they're trying to attract each other. Or your clothes in your clothes dryer, and you pull them out, and your silky type stuff is right against your cotton stuff, and you have to rip them apart almost, not rip them, but pull them apart. That's static electricity. It's not moving charges, it's static, fixed on the thing. So this is Coulomb's law of electrostatics. the thing with the electroscope. You know, that was static charge. Here's what it states. The force between 2 point charges I abbreviate like crazy, Q1 and Q2, and by the way, that's what we're going to use to represent charge. Little symbol Q. What Q1 and Q2? 2 charges. Is directly proportional directly proportional to the product of their charges, Q1 times Q2, product, and inversely proportional to the square of the distance separating them. There's the inverse square law. Square of the distance between them. And I think they call that R. I'm sorry, I was going to call it D. R. Okay. Now, written as a formula, which they do next, it's this. F, now this is the Coulomb's force, so I want to call that F sub C for Coulomb's force. Like the book used to call F sub W for weight, and F sub C for Coulomb's force. And this will be Q1 times Q2. Okay, wait. Remember it said proportional? Then you have a constant of proportionality. And that constant proportionality is called K. And it's K times Q1 times Q2. So directly proportional to the product of the charges, inversely proportional to the square of the radius. There is Coulomb's law. Okay? Now, this K is actually called the, sometimes called the electrostatic constant, okay? Sometimes called Coulomb's constant, various names like that. And I'm trying to think what your book calls it. They don't call it anything. No, I'm sure they do. I'm trying to find the table that lists it. Common physical data, back inside cover of your text. Electrostatic proportionality constant, K. You see that just about the middle of the table. Okay? And there it is. That's what they call it. Sometimes called Coulomb's constant, but they call it electrostatic proportionality constant. What a name. And that value is 9.00, okay, pretty precise number, times 10 to the 9th, okay. Now it has units with it. Because on this side, force is measured in newtons, so it's got to have newtons here, so you have newtons on both sides. I know it'll come back, I think. Yeah. Every time this moves, it disconnects it for some reason. I don't know why. I tried to hold it, but I wasn't holding it at that time. Okay. It has to have something to equalize. These are measured, the radius, or the R distance between is in meters. And since that's in the denominator, you have to have this up here so you can cancel those out. So that's meter squared. And then this is Coulomb times Coulomb, so it's per Coulomb squared. So that's the unit for it. Newton meter squared per Coulomb squared. Okay. A pretty good sized number. 10 to the 9th, that's billion. Okay, 9 billion, Newton meter squared per Coulomb squared. All right. Now, just to give you a relative idea, the force due to gravity, we talk about that. Not the acceleration due to gravity, the force due to gravity. its constant, which they call capital G, and you can probably find that in the back of the book too. Yeah, there it is, number 2 in that same table. It's 6.67 times 10 to the negative 11 Newton meter squared, but that's per kilogram squared. Kilogram's a lot bigger than a coulomb, but they're measuring different things. But still, 10 to the minus 11 rather than 10 to the positive 9, that's about a 19-fold difference of magnitude. So electrostatic charges are actually stronger than gravitational charge, attraction, except for the fact they don't go as far. Gravity can travel across the universe, okay, well, almost. Across the solar system anyway, across the galaxy anyway. But electrostatic charges are not nearly that far in advance. So, let's go to example 1. You got Coulomb's law, law of electrostatics. Okay, all right to erase? Yay? All right. 2 charges, each with a magnitude of 6.50, and they're both positive, by the way. Microcoulombs. What in the world does microcoulombs mean?
Micro mean
10 to the, it's a millionth. 10 to the minus 6. Okay? So we'll write that in a second. Separated by a distance of 0.2 centimeters. So your R, and this, by the way, this is Q1 and Q2. They're both the same charge. R is 0.200 centimeters. Now that's pretty small, folks. Okay? Of course, that's a pretty small charge, too, microcoulomb. Just to get an idea, I've got 2 dimes. Oh, I feel rich today. Each of those dimes is about 1 millimeter, and 0.2 centimeters would be 2 millimeters. That would be the distance they're separated. These charges are really close together. Okay, really close together. All right. It says, find the force of repulsion between them. Why repulsion? They're both positive charges, and like charges repel each other. Okay. So the force due to force of repulsion. Now what we need to do, folks, is get them into our metric units, because the Coulomb's electrostatic constant is in metric unit, is SI units. So this is 6.50 times 10 to, remember what I said micro was? Minus 6 coulombs. Okay? And you got 2 of those, Q1 and Q2. This is 0.200 times 10 to the centimeters is minus 2 meters. 100th of a meter. Okay? 10 to the minus 2. What's that?
Where you get the 10 to the 6 from again now?
What's that again?
10 to the 6 at the top.
10 to the minus 6. Because that's what micro means.
Oh, okay.
Yeah, microcoulombs. Instead of micro, you put 10 to the minus 6. Instead of kilo, you put 10 to the 3rd. What's that? Yeah, if it was mega, that would be million. That would be 10 to the positive 6. You're absolutely right. So, what's the force due to electrostatic attraction? Or the repulsion in this case. F, this is Coulomb's law, is equal to 9.00 times 10 to the 9th, remember? Wasn't that right? And that was Newton meter squared per Coulomb squared. Multiplied by 6.50 times 10 to the minus 6. I can't write. Let me clean that up a little bit. My screen is sort of bouncing on me a little bit, so it's hard to keep the pen on the page here. 10 to the minus 6 coulombs times 6.050, I can't write, times 10 to the minus 6 coulombs, because you got two charges, Q1 times Q2, divided by, ooh boy, look at this number, 0.200 times 10 to the minus 2 meters squared. Now what you could do if you wanted to, if you want to make this number a little bit larger, like 1 larger, drop this by 1 and make it 2.00 times 10 to the minus 3. Would you rather do that or leave it like it is? Huh? Okay. Might be a little easier to deal with if we did it the second way. So let's take that 2.00 times 10 to the minus 3. Whoa, where's my pen? Come back here, pen. All right, 2.0, so I don't need that leading 0. 0 times 10 to the minus 3 meters squared. Like I said, it's like 2 millimeters, which is 2 times 10 to the minus 3. All right, pull, yeah.
Is that a 3 up there?
Okay.
Where the R is? Oh.
Okay, yeah. I moved it. Remember, I said what we had before was 0.200 centimeters,
Okay.
which is 10 to the minus 2. If you move your decimal here, so it's 2.00, you made this bigger, drop that by 1, and that made it minus 3.
Okay.
A minus 2 minus a 1 is a minus 3. So it was a sleight of hand that I did there, and ugly writing, okay. So let me adjust that to, it's not that, okay, there. Now my decimal is right there, 2.00. Okay. All right, pull out your handy dandy calculators with scientific notation. Let's see if we can get this done. You don't have to put the 0.00. So 9 EE or EXP 9. Remember how to do those? Don't do times 10. Do 9 EE or EXP 9 times 6.5 EE or EXP negative 6 times 6.5 EE or EXP negative 6 again. Now remember, when you do your negative 6 there, you use that little minus sign in parentheses, not the subtraction key. The minus sign in parentheses. Okay, divided by 2 EE or EXP negative 3, but that, before you do anything else, square it. And then hit enter, or equal, or whatever.
Too fast for me. I gotta
Okay. You want me to write them out?
Yeah.
9, which does your calculator have, EE or EXP?
EE.
EE. 9 EE 9 times 6.5 EE negative 6. Now make sure that negative is the one that's in parentheses negative, not the subtraction key. Times 6.5 EE negative 6, then divided by 2 EE minus 3, and be sure that's in the parentheses, minus 3. Minus 3, I wrote it too high. But then before you do anything else with that, do your square key. I think that says x squared or something like that. That's the key that you press. And then you hit equal. Now if that doesn't work, I'll tell you one modification you could do. Anyone get an answer? What did you get? 9.51. Okay, you got 95100. Yeah. Is that what you got?
I got 95062.
Oh, okay. 062.5 or something, right? Okay, yeah, that makes sense. So how many significant digits we got? 3. 3 here, 3 here, 3 here, 3 there. 3 everywhere, okay? So it's count all three significant digits, 1, 2, 3. Look to the right, that's a 6. Bump this up to 1, and that would be 95,100 newtons, because look at your units
You
here.
have to move the decimal back over.
Okay, okay. Here's the decimal here. If you want to move it to get scientific notation, you move it 1, 2, 3, 4 places. So that'd be 9.51 times 10 to the 4th newtons. That's a lot of newtons.
It is. Oh my goodness.
Yeah. 95,100 newtons. Okay. I take it this is Cavante, right? Okay.
Can I talk about the class?
Pardon me?
I need to talk about the class.
Yeah. Okay. Want to wait till right after class? Okay. All right. I also have a question. Are you also enrolled in my
Yeah, I just got
Physical science?
Physical science.
Yeah. You know, every class is like a week. So we're several weeks into the term.
I'm going to talk about all of them.
Okay. All right. All right. So that's how many newtons. Oh, let's look at the units. Notice this was Newton meter squared per coulomb squared. Here we have a coulomb and a coulomb, so that wipes out the coulomb squared. Down here we have a per meter squared. That wipes out the meter squared. So sure enough, we're left with coulombs. That is a large amount of force. That's what's holding those two charges. And these are microcoulomb. This is small amounts of charge, but holding them or repelling them quite strongly. So in order to keep them that distance apart, you're having to really push them together big time. Okay. And that's it for 17.3.
I have a question. How do you do that until exponent on your calculator?
The EE?
That.
Oh. How do you go from this number to that? I'm not sure. Let me see your calculator.
There's a way to do that on the calculator.
Some will automatically do it, some may not. Let me see. Oh, up here, the scientific engineering.
Oh,
What did you have? 95062.5, right? 95062.5. Okay? Now, if you press this key here, that second button, we want scientific, and press enter. There it goes, another equal 9.5, 10 to the 4.
Okay. All right. Thank you.
Anyone else? Okay, good deal. Okay. That finishes 17.3. Okay. Problem set for 17.3. There's 8 problems there to do any of the odds 1 through 7. Shouldn't take too long to do quite a few of those. There are not that many, and there's not really all that much difference. All right. Any? Yes.
Well, all of our tests are taken on too.
Yeah. Including the final exam. The final exam is just your last test, huh?
I was just going to ask you the final exam. Will we have all these formulas?
Okay. The thing is, the final exam is just going to be the last chapter test.
Oh, okay.
We don't really have time or the convenience of really getting everything finished and then having a comprehensive final. It's just not with a class that just meets once a week, so we got to be covering material right up until the last day. And then I'll give you the last test and tell you how many questions to do. All right, good deal. Okay, so let's move to electric fields. So I'm going to clear this screen. I still haven't seen that next slide. There it is. Whew. Okay. 17.4 is talking about electric fields. And, did we have this one? I think we did. Yeah, it was 3 and 4, I'm pretty sure. I have to keep in mind. Yeah, 3, 4, and 5. Okay. So far, we've discussed electrification due to brushing electrons from one surface to another surface. In terms of static electricity, an electron field exists where there's an electron force, whether of attraction or repulsion, okay, acts on a charge brought into the area. So let's just say we have some region here. You want it positive or negative? I don't care. Positive. Let's say this is a positive, some sort of positive charge here. Now you're going to bring some charge from way out somewhere. This will be a very small positive charge from outside. And you're bringing it in. What this is, this has a field around it, and the field is doing this. And these arrows are in the direction of what a small positive charge or field. So this small positive charge out here is feeling pushed away big time because the electric field is pushing outward. Now, if this had been a minus charge, then these arrows would have all reversed, and the field would have been pulling in. Wait, I meant to have my eraser. Okay, if that had been a negative charge, the field is then pointing toward it. So it would have been, and this is what a small positive charge would feel like being pulled in. So in other words, this small positive charge then would feel like it's being pulled inward toward that charge, toward that field. So now it would feel like it's being pulled inward. So the electric field exists where there's an electric force, either of attraction or repulsion, acting on some small positive charge brought into the area. Okay? Now, I don't know if you've ever seen someone do this. I've never done it myself. But if you have a balloon, you know, with air in it, you know, balloon, and rub it against your hair. Now, your hair needs to be clean, not greasy, and it needs to be fairly dry conditions. Sometimes this won't work in the South, okay, because there's just too much humidity. But rub it against there and then put it against the wall and it'll hang on the wall. Stick there. Why? Because you rubbed electrons off your hair onto the balloon, just like fur onto rubber, okay? The balloon is sort of rubbery. Fur, your hair is sort of like fur. And onto the wall, onto the fur. So it has an excess of negative charge. The wall is neutral, so it hangs onto it because it's an attraction. There was a field around that balloon that attracted it to the wall. Okay? I thought that was a pretty lame example, but it is true. They have a picture of it in the book. Okay? Now.
So that's what I have nothing like balloons that stick to your leg.
What's that again?
Balloons that stick to your leg.
Yeah, same type reason. Okay? Because they get charged. And that's
I'm learning this stuff. I just don't see why we have.
Yeah, and that's the same reason that sometimes lint will be attracted to your clothing and stuff, because that's small charged particles that get attracted. Dog hair. We have a golden retriever, and boy, that attracts like crazy, okay? And I can actually rub her sometime in very dry, usually cold day. I can rub her real hard. I can hear it go. I can feel the little tingle on my hand when I'm doing that. It's not much, but a little bit, okay?
When you were saying, like, positive charges, you know.
Okay, the positive charges is just where you move the electrons away from something, leaving a net positive charge. You never move protons. Protons are part of the nucleus. You'd have to have a nuclear reaction to move those. You don't want to have those, okay? What you move is those electrons that are surrounding it. And if you move them away, that becomes a positive charge. If you attract them, that becomes a negative charge. So that's how you get your charge, either gaining or losing electrons. Always gaining or losing electrons. Okay. Now, the convention here is that the electric fields always point away from a positive charge toward a negative charge, like I just showed here. The figure they show in the book is, and they actually do a lot better job. So let me start back over. I think I'll erase the whole thing and draw this. And rather than a single positive charge, you have positive charges all around. Yeah, okay. All these are positive charges. And this is where positive charges usually live. They live on the surface. These should be all positive. They sometimes look like time signs, but I just don't draw well. Okay? So therefore, the electric field is always pointing away. And by the way, the electric field is given the symbol E. Clever name, right? It is a vector quantity, so I usually put an arrow over it. Now, as we just said, an electric field exists where you have the charges, the forces on a net charge. So the electric field is equal to force, which is also a vector quantity, that's Coulomb's force, divided by your charge. And that's always a small positive charge. It's called a test charge, and they put a prime by it to indicate it's not the same as the charge here. That would be some larger charge. This is a small positive test charge. Okay? And the charges are measured in coulombs, so therefore the electric field is measured in newtons per coulomb, because it's newtons here divided by coulombs there. Newtons per coulomb. That's what measures electric field. That's the unit for electric field, newtons per coulomb. All right, let's do example 1. Red-eyed? Okay. A positive test charge of 30 microcoulombs. So this is your Q prime is equal to 30.0 microcoulombs. Okay? Now, do you want to write that in terms of coulombs? It would be 30.0 times 10 to the, what is micro? Minus 6. Minus 6 coulombs. Okay? It's placed in an electric field. The force on it is 0.6 newtons. The force, I'm going to call it Coulomb force, is equal to, the book just uses F, and this, by the way, is a vector quantity, and that is 0.600 newtons. Okay? What is the magnitude of the electric field? So as soon as they say magnitude, you can forget about the vectors. They don't really care about the vectors. What's the magnitude of the electric field at the location of the test charge? So we're looking for E, and what is E? F sub C divided by Q prime. So this will be 0.600 newtons divided by 30.0 times 10 to the minus 6 coulombs. Pull out your handy-dandy calculators and get you ready for a surprise at how big this is. To something.
Well, I did answer. I don't know it's coming up as an exponent.
It is coming up or not?
The way I put it in.
It is coming up as exponent. That's probably okay. And what do you get?
2 times 10 to the negative 8.
Ooh, no, you didn't do something right.
Yeah.
Okay. Oh.
Did I put the negative part in wrong? Not 0.66 divided by 30.0.
Okay.
Okay.
Times 10 to the.
Times.
No, okay. You don't need to do the times 10. You do your EE.
Oh!
Yep.
Okay, shift and then the E. And then do 6, right?
Then do the negative 6. Yeah.
Negative 6. 4.374.
Say again?
4.374.
Oh, okay, something's still wrong there. Okay. Let me see what you got. 0.6 divided by 30 EE.
You have to put the EE twice?
No, the
Just
EE key.
Yeah, I just put second
That
and first
second,
E
that
once.
right. Mhm. And then you have -6. No,
What is
okay,
that in there?
Yeah, you still had that in there from before.
Oh.
So I don't know how you get rid of that.
You just take it out.
Yeah. Let's see, that doesn't take it out.
Clear.
Clear that. Ah, there it goes. Okay,
Just
now
hit
you
enter.
see, that was still hanging around.
Okay, it's still coming up with the exponent.
Okay, and what is it?
2.00
times 10 to the.
No, it don't have all those zeros.
No. Well, no. I put the zeros in because we had 3 significant digits. It's just saying 2
2 times 10, 0 to the 4th.
to the 4th. That's it, exactly.
Okay.
And I put in the zeros there because we had 3 significant digits there, 3 there, 3 there.
So we're supposed to be using the EE symbol when putting that in like that.
Well, you use the EE when you're dealing with exponents.
The exponent, okay.
Yeah.
Let me write this so I can remember.
And that's measured in newtons per coulomb. That's the units for electric field. So that was a very small charge. I mean, a very small force, 0.6, and a very, very small test charge. In fact, that's why it's such a large field. And that gave you a pretty good size, all right, take care, electric field. 2 times 10 to the 4th, that's 20,000 Newton per coulomb. That's a lot. Okay. All right.
Well, basically, if we just put it like that, that is the answer, that would be fine.
Yeah. But you put the significant digits in there. That gave you 2, and then you know you have to have 3 significant digits to put a decimal 00. To give you 3 significant digits. Newton per coulomb. All right. Now, back in the old days, maybe some of you remember grandmother had one like this. I'm just kidding, sort of. Televisions that sat, you saw the screen here and they sat away from the wall about that far because they had a big box behind them, you know, things. Okay. I don't like that anymore. Now televisions are about that thick, right? Completely different technology. But what you have there, what you had before, you were firing electrons at the screen and you were deviating them by changing fields and stuff, and that's what put your picture there. Nowadays, it's plasma. I can't even tell you how that works, okay? That's so much new technology beyond what I have. Now this guy, this is showing physics connections here, and it's lightning safety. And it's a guy on a golf course, and evidently it doesn't look like a thunderstorm is anywhere close. But this is imagining it is. What do you do if you can't get inside? Get as low as you can. So this has him down in the sand trap. He's at the edge. He should be at the bottom of it. And squatted down so he gives the lowest profile possible. Wouldn't it be better to run over to the trees there and get out of the rain? No, the trees are lightning rods. You don't want to get under a tree or anything like that. So actually, lowest you can go, get as low as you can, and get out. So they do a little thing on lightning safety. You don't have to read it, but it's an interesting thing. Problem set 17.4. We've already finished that. Do any of the odds 1 through 7. Okay. Now 17.5, we're going to be talking about simple circuits. Okay? All right. Simple circuits, 17.5. All right, to erase this one. Okay, we really have 2 types of electricity. Y'all know what they are? Say it again.
Direct current.
Yes. And alternating current. Is anyone using either one of them in here in the room today? What? Okay. The lights up here, the fluorescent lights, and I'm guessing the projector. That's alternating current. Okay? Well, I'm plugged into the wall there. Am I not using alternating current? I am up until this box. What comes in here is, if I can get it untangled here, okay, is alternating current, but this is a converter or a transformer, what do they call it? Adapter, that adapts from AC coming in to DC going out. Computers, cell phones, she was talking about she couldn't charge her cell phone, that's DC. And guess what? Every one of those chargers has a box on it that you plug in. That changes it from alternating to direct. Okay? Anything that has a battery. This has a battery. It's not a very good battery, so I have to have it plugged in. Her cell phone has a battery. Cars have batteries. Those are all DC. Okay? Flashlights, battery. Even the flashlight you plug into the wall to recharge, it has one of those converters on it because there's an interior battery there. That's DC. Anything running like the lights here and probably the projector, because I don't see any box on it, that's AC. Okay. So those are two types of current. Direct current and alternating current. Now what's the difference? Direct current is always, just like a battery, has two poles, a positive and a negative. So the charges, and there's a problem here, thank you Benjamin Franklin, the charges are always moving from one to the other, but in one direction. There's a debate on which direction they actually move, but we won't get into that. But they always move in one direction, because that's the only direction they can go. Alternating current, however, that's made generally by a generator, something that's spinning, turning, and what you have then is half the time it's positive, half the time it's negative. So these charges that are going through here or through there, they're just going back and forth, back and forth, back and forth, back and forth. They're not traveling down the wire at all. All the charges in the wire just doing this all the time, okay? That's where the energy is, and that's what creates that. Direct current, the charges are actually moving in the wire in one direction. Pretty much, okay? So that's the difference, okay? The drill they show here, you don't see a cord on it, do you? That means it's got a battery on it, DC, direct current. The flashlight, don't see a cord on it, therefore it's DC. Now, a extension cord light, that would be AC. The flashlight with no cord, DC. Okay. Now, an electric current, a circuit, is a conducting loop. When they say conducting loop, that means there has to be wires or something connecting. Conducting loop and charge, and it has to conduct charges. So it's a conducting loop, and here's how we represent some of the elements. This will be for a DC. So usually we have what they call a battery, and the symbol for that is one long line and one short line. Okay? They call it a dry cell battery. That's usually what's in most flashlights. In your car battery, that's a wet cell battery. There's liquid in there, and it's pretty strong liquid you don't want to mess with. It's sulfuric acid. You don't want to spill that on your clothes, otherwise you have some holy clothes, okay? If you have any clothes, it'll eat them up, okay? Then it goes through the circuit, and these are wires. Now, you don't have to have sharp corners like this, but they always draw them that way, until you get to your light bulb, okay? Now, they represent a light bulb one way. Later, we'll do it this way. It's a resistance inside a circle, so that's like a light bulb, okay? And then you go over here, and somewhere on the flashlight, you usually have a switch. So the switch here would be open, and there the bulb wouldn't come on, because there's not a complete circuit because of that open switch. Close the switch, turn on that light thing, then the bulb comes on. Okay, so you could draw this in the shape of a flashlight, would have made more sense, but they drew it like this because that's sort of standard. Okay, now, it's really not the charges moving that makes the light bulb come on. It's the energy from the moving charges that makes the light come on. It's all an energy issue. So the source of the energy, the source of the object that provides the electrical energy for the flow of electric charge, are the electrons in a circuit. The dry cell here is doing it. Now they haven't really, yeah, they are going to do it in a minute. We'll get there in a minute. I won't get into it now. So what happens, they have a diagram at the top of page 461. And they start just like they here with a battery, a cell generator, an outlet, or some other device that is going to start moving charges, giving what they do that gives the charges their energy. That's what's happening. Okay. So you have low energy electrons on one side, higher energy electrons on the other side. Here's the deal, folks. Electrons are what carry the charge. Okay? Whether they're just going back and forth, back and forth, back and forth, or if they're actually moving in one direction. Electrons are what carry charges most of the time. Now remember I mentioned your lead acid battery in your car? Actually, inside the battery, in the wiring of your car, it's electrons. That's all, moving those around. But in the battery itself, it's actually ions. Remember when I was mentioning ions? They're charged particles. Okay? You have positive ions going one way, negative ions going the other. That creates a difference in charge, which we call a potential difference. We'll get to that a little bit later. We're not doing it now, but right now. So that's why they say you have low energy electrons here, high energy electrons here. The battery is what gives them, boosts that energy up. Okay. So that is your electric potential energy. That energy that your battery or your generator or whatever is giving to the charges. Okay? That's your source of the energy, your electric potential energy. And you always have to have a change of potential in order for charges to move. If you don't have a change of potential, they're not going to move. Just like if the book is right here on the desk, it's not moving. If I lift it up here and drop it, it's going to move, and it's going to stop when it hits the desk, okay? Because it has a change of potential. More potential energy up here because I lifted it. I did work to get it up there. When I release it, then that work energy is given back as it comes down. All right. There is an analogy here, and this is all it is an analogy. So let's end this and go to this one. This is how far it took in chapter, no, we did those others, but this is the first one we've had in several sections. Oops, what just happened there? Okay, so let's go from current slide, and here we have it. This is just an analogy, folks. Oh, what we have here in the battery is, to me, this is really fuzzy. I don't know why. I think the projector is just not very well focused. It may mess it up. But let me. Tell me if it gets better or worse. All that does is make it bigger or smaller. Here we go. Worse? Better? Right about there? I don't know if it'll stay that way or not. Sorry if whoever sits in the chair. That is a lot better down here. Okay. Y'all are good. Okay. So, in your battery, we have a chemical reaction going on. That's what is in there. Sulfuric acid dissolves the lead that's in the plates of the battery and moves the charges around. When it dissolves them, it gives some positive charges, some negative charges. The electrons, now, here's the problem. In just about everything else in physics, things move from high potential to low potential. The electrons are negatively charged, so they go in the opposite direction. So you're giving the electrons high energy here, lower energy here. So the electron's energy is being boosted here. That is the potential difference of the battery. So then electrons, high energy electrons, flow here, go through the light bulb, lose some of their energy. It becomes light energy rather than electrical energy. And then the low energy electrons come back and get boosted up again. And that's what's happening every time you turn on the light bulb. Now here's the analogy. Let's pretend that we had a water pump here, okay? And you're pumping water up and giving it potential energy, putting it up in the tower here. That's what, the big old peach at Chilton, at Clanton, right? Okay? Or any water tower you happen to see. You've given that water energy, gravitational potential energy way up there. And then you turn on your faucet and the water down here blows at a pretty good rate. If you put a turbine here, you could generate electricity or something, okay? And then the water returns and you go over and over again. Well, that's sort of like this. The pump here that gives water its potential energy, the battery is that giving the charges their potential energy, electric potential energy, okay? And then the pipes are like the wires here. They allow the water to flow or the electrons to flow. The load here, this is your light bulb, that's giving off light energy. Here's your turbine that is turning a fan or doing whatever it's turning. That's like your light bulb, okay? And like all analogies, this will break down if you get too serious about it. If you were to cut the pipe here, you'd have water spewing out everywhere. If you cut the line here, everything just goes off. You don't have electrons spilling onto the floor, okay? That doesn't happen, okay? It just stops flowing, okay? Make sense? That's just the water pump analogy to a battery in a circuit. All right. Now, that's going to be several pages away, I think. Goodness gracious, several pages away. Yeah, okay. So let's go back to our other one, and we'll pick up from there. I have to get my pen back. Okay. Oh, goodness gracious. Running out of time here. The conductor, which we called the wire, okay? Or anything that is moving the charge. The conductor carries or transfers the electric charge to the load. Okay? Kind of true. It is true. The light bulb, that was what we were doing there. The conductor is a material such as copper. That's one of the better conductors. Not the best. The best conductor is actually silver. Well, why don't we use silver wiring? Any guesses? Way too expensive. And what's more, copper bends really easily. Silver is pretty brittle. So you wouldn't be able to have wires that would be flexible. They'd all be stiff, you know. So, copper. And the difference is very small. Silver's better, but just a little bit better. Next after copper is aluminum. So if silver was here, copper here, aluminum's way down here. So these are very close. This is not nearly as close. Okay? So the conductor is any material such as copper, usually metals, not always, that through which the charges move fairly freely. The electrons move fairly freely. Okay? So the higher energy electrons move from the higher energy source to where it's lower energy. That's what makes them move. Now, they have a pretty neat picture in the side of your book. Do all of you have books? Oh, you don't. Okay, I'll try to draw this. And this isn't a completely accurate picture, but I'll try to do it. If these are your little charges here, okay, and these aren't really represented too well, and every one of them is going in this direction. If they go through in that direction pretty easily, then this is called a conductor. Okay, a good conductor. If, on the other hand, this was something like a ceramic rod or something like that, and you did happen to have some charges here, if these charges, in order to move, just gets bounced all over the place, you know, as they try to move, that's a really lousy conductor because it's hitting resistance every time they try to go. Up here, very little resistance to the flow. We're going to hit those terms a little bit later. So these are called conductors, these are called insulators. Okay? Or non-conductors is another word. Now, there's another device, and they mention it here, a small number of materials called semiconductors. Have you ever heard that term before? Second? Yeah, it's partial conductors. They fall in between conductors and insulators in their ability to conduct electricity. Their importance is due to the fact that these materials, under certain conditions, allow current to flow good. They become good conductors. Other conditions, they suddenly become insulators. So they're semiconductors. And they usually allow current to only flow in one direction. Silicon is a semiconductor used in transistors and integrated circuits. Those are called ICs. They're neither good conductors nor good insulators in their pure form. However, they become excellent conductors or insulators when an impurity is added, which is really bizarre. So you have these, you layer the semiconductor materials together. Selenium is a semiconductor used in making photocopies. And, you know, we use those all the time. Now, there's one more, and this is called a superconductor. Okay, superconductor. What's that? Well, that's something that in certain circumstances, and usually this involves incredibly cold temperatures, suddenly they offer no resistance at all. Even in your conductors, you have a little bit of resistance. Even the very best conductors, a little bit banging around. Okay? In a superconductor, no resistance at all. Wow, that would be neat, wouldn't it? But you have to have such incredibly cold conditions for that to work. Which is it's just really bizarre. Material that continuously conducts electricity even when you don't put a voltage on it. Once you get it wrong, just take the voltage off and it just keeps moving. Usually near absolute zero, so awfully, awfully cold. Heikki Kamerlingh-Onnes discovered superconductivity in 1911, shortly after he discovered how to liquefy helium gas. He determined that mercury metal lost its resistance to the flow of electricity at temperatures just below 4.2 K. That's 4.2 above absolute zero, whereas room temperature is about, trying to get my numbers right, 293 K. Okay, so 4.2 as opposed to room temperature 292 K. Superconductivity, 4.2K. That's awfully cold. Awfully close to absolute zero. Now, over the years, I'm pretty sure he won a Nobel Prize in physics for that. Over the years, there's been, I think, at least 4 more Nobel Prizes as they found better and better superconductors that came at warmer and warmer temperatures. When I say warmer and warmer temperatures, nothing up here, just going from 4.2 to maybe 30, or something like that. Still awfully cold. Okay. So that's superconductivity. Sadly, we're out of time. How dreadful. And what's more, we won't meet again for 2 weeks. Next week is spring break week. Did you know that? You didn't. So you're going to be here next week, right? Okay. So we'll pick up next time with the load, and we will go from there. Now I've got to find my marker so I can know where I am. Here we go. All right. Okay, surely. Okay. It's pretty dreadful. I hope you're ready for it.
Oh, really? I just folded it.
Okay, that's
I
fine.
didn't put it right here because there's a lot. I wrote it on there.
Okay, that's fine. Super. Thank you. Okay. Anyone else want to see their scores? I'll go on and turn off the recording so we won't be recording.